Well, we'll get started. I want to, first of all, welcome everybody to this CAST-supported, sponsored lecture series. We are very, very pleased to have our guest, Paul Mayencourt. Paul is actually coming to us live from San Francisco, actually Berkeley, California. And we're very excited because Paul here is actually has been in touch. We've been in collaboration and dialogue with Paul now for almost 1.5 years, or even 2 years, trying to align his visit with us. But unfortunately, due to the pandemic, Paul has had to not been able to visit until recently. And we've instead elected and created space to allow him to provide a workshop and also a lecture on his research topics. The work that we will be talking about, I'm just trying to see how to move slides here, apologies. So Paul is actually one of many CAST visiting researchers and residents. The program that the facility for the Center for Architectural Structures and Technology has been running for about 20 years now. And in its most recent incarnation that started about 8 years ago, Paul has applied and as part of some postdoctoral research to do research here at CAST as a part of his research project that is coordinated with the University of California, Berkeley, and also recently from his alma mater at the Massachusetts Institute of Technology in Cambridge. And the research that Paul is going to be speaking to us about is part of his ongoing work that started at MIT on the topics of maximizing the use of low-grade timber structures to explore the possibilities for carbon sequestration and optimization possibilities in structural design, and also as a way to achieve greater efficiencies for our building and design trades. Paul is a lecturer at the College of Environmental Design and a researcher in the Department of Environmental Policy, Science, Policy, and Management at the University of California, Berkeley. Paul has a PhD in architecture and building technology from MIT and a Master's of Science in Structural Engineering from the Swiss Federal Institute of Technology in Zurich, ETH Zurich. And Paul is a colleague here in part also because he's worked closely with his main advisor, Caitlin Mueller, who's a friend of CAST. And Caitlin has worked with us on a couple projects, most recently in 2016 on Fabrigami that we partnered with the Fab Lab, and Caitlin and Paul found out about CAST through that project as well. So we're very honored and happy to have Paul here. And to follow this lecture, Paul will introduce briefly this topic of this lecture workshop that he'll be offering on May 9th through 11th. It's a 3-day workshop on structural shaping that he'll be doing using digital tools and in partnership with the Fab Lab here at the University of Manitoba. We will be creating space here in CAST to do a hybrid version where Paul will be offering the workshop remotely, but we will have a space set up specifically for workshop participants. There will be information forthcoming on that workshop, so keep your eyes peeled for that. I want to take a moment to acknowledge that we are on Treaty 1 territory and that the university campuses are located here on the homelands of the Anishinaabe, Cree, Oji-Cree, Dakota, Dene people, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories, and we acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. And we will have Paul give his presentation. There will be a bit of a pause between 2 sections, at which point Paul will be happy to take a few questions if there are any from the audience. And at the end, I'll help to moderate some Q&A for Paul when he's done the full lecture. So I will stop my screen. And without further ado, Paul, I welcome you and see if your screen can share there. Perfect.
Great.
Okay, thank you.
Thank you so much for the introduction. And thank you everyone for coming on this online lecture. I'm very happy to be here or remotely here, I guess, and talking to you about my research, and very excited to be part of the CAST residency program and coming in I think about a month to offer a workshop. And some of my research I'll be showing today is what I'll be also like, kind of infusing into the workshop, and that's going to be kind of a preview of the workshop in some ways. So as Lancelot said, I'll have maybe 3 sections of the lecture, and I'm happy to take questions at any time, but I guess between the sections is a good time if you have any burning questions, and otherwise we can have a discussion at the end. My lecture is focusing on designing for low carbon timber across scale. And I'm going to talk about different scales of design. And the first one will be building elements. And I'm going to go all the way to forest ecosystems and how we can consider forests into how we think about buildings. And I just want to start a bit with my background. I grew up in a country where there's a lot of forest and a lot of mountains, and traditionally is somewhat understood as being a place where there's a lot of timber construction, but I think it's not so true anymore. And a lot of my research is focusing on mass timber and timber construction. And even in a country that has traditionally a lot of timber houses or, traditional timber construction, mass timber is being a new material for a lot of people. And right after my master's thesis or master's degree, I went to work as a research assistant in the laboratory for timber construction. That's when I become, I'd say, a wood nerd, and have this passion for timber. It kind of switched my interest to the timber construction. So here you can see me on an origami shell that I built and tested when I was a research assistant, and you can see me preliminarily load testing it and kind of jumping on it to see how sound the structure was. But right after this, I worked as a structural engineer in an office in Zurich for about 2 years. And every morning I was going through a train station designed by Santiago Calatrava, and you can see here an image of one of the columns that supports the roof on the platform. And I was really fascinated by this part of the structure. If you look at a cross section and like an elevation of the left element of this construction, so the column, you can see it has some sort of changing section. So at the center, the section is bulkier and bigger, and at the ends, this is slightly smaller. And this section is changing throughout the elements as to maximize the use of material, but also kind of showcase the structural behavior of the element to everyone and to be on display. And what was kind of sad and also funny to me at the same time is that I was also working on train station designs as a structural engineer, and I was designing the columns of the train station in Bern, which is the capital city in Switzerland. But the design of the columns were kind of imposed on me, and this is the section that it looked like. And you can see it was a bit frustrating coming from school, and I had all these ideas about optimization and how we could combine structural design and architecture. And I was walking through the train station every morning, but I had to work on something that was slightly less optimized. And I kept wondering why we couldn't, use these techniques of optimized and structurally expressive structures in everyday structure to save material. And especially, we all know that the built environment is responsible for a large amount of carbon emissions globally. So 40% of global carbon emissions is coming from the building sector. So this is a large opportunity as actors in the built environments to do something about it and have an impact on how the future of our planet is going to look like. And these carbon emissions are separated in embodied carbon and operational carbon. And as we build more efficient or carbon efficient buildings in terms of energy use, the embodied carbon, so the energy that is required or the carbon required to build a building is becoming an heavier or more important part of our construction. So both the operational and embodied carbon are very important, but my work focuses on mostly embodied carbon and how we can reduce the embodied carbon in construction. So after working for 2 years, I went to MIT to do a PhD, and I was really interested in pursuing this idea on structurally optimized or using new technologies such as optimization and computation and digital fabrication for everyday structure to have an impact at scale. And this is an image that resulted from my PhD, where you can see some elements that are somewhat familiar to people that know mass timber construction or construction in general, but are also a bit different. And I'm going to talk more about this a bit later, but you can see here some of the ideas of how to apply these ideas at scale for everyday building. So my talk is going to have three main parts that are organized into three design scales. The first design scale is going to be about materials and building elements. The second scale is going to be moving to building systems, so how you can transfer some of these ideas to building elements connected together into a building system. And finally, how we can consider ecosystems or material sourcing as part of the design process in buildings to lower the impact of construction. And maybe the last scale is closer to what I'm doing now as a researcher at UC Berkeley. So I'm part of the Department of Environmental Science, Policy and Management, that we also call the Forestry Department, where I work on the use of local California forest. So the first part I wanted to talk about is the kind of research areas that I'm focusing on and in research interests. So I have three main research interests. The first one being creative structural design. And I know at CAST, this has been something, that's been pushed in research a lot. Some of my work has also been inspired by researchers at CAST, and one that I can name for sure is Mark West with the work on shaped concrete beams using fabric formwork. And I would say that some of my work is adjacent to this and taking the same inspirations of how can we do more with less. And I'm also combining this interest with low carbon timber structures or low carbon materials in general and advanced digital manufacturing. And this is not necessarily a research area that I have now, and I'm not going to show too much in this, but this is something that is going to be leveraged to allow for new structural ideas and the use of or the deployment of low carbon materials. The first scale I mentioned is materials and building elements. And I'm sure some of you heard about mass timber. It's a fairly new construction or material system that has a lot of promises to lower the embodied carbon of buildings. And you can see here an example of a typical mass timber building that has glue laminated columns, glue laminated beams, and CLT panels on top. And mass timber has been kind of perceived as a low carbon material for a lot of good reasons. Tree, when they grow, absorb carbon in their fibers. So you can imagine wood as being solid carbon to some extent. The main products that will be used in these construction systems is glue laminated timber. You see here on the left. So cutting smaller trees into boards or 2x4s or 2x6s or dimensional lumber and then glued together into larger elements. So it has enabled us to go after different timber resources in the forest, not having to cut big trees, but we can also cut different trees and glue them back together into creating larger structural elements. And cross-laminated timber, that is not such a recent innovation, but the way it's been coming to the market is fairly recent in many places, maybe 10 years or 15 years ago. And the only difference between glue laminated timber and cross-laminated timber is that the cross-laminated timber has cross-lamination. So some of the boards are going at 90 degrees from each other in order to have dimensional stability. So wood will move with changes of moisture contents, humidity in the air, and the cross-lamination, so the layers of the wood being crossed, will increase the dimensional stability so that the panel is going to be more stable in space when moisture is changing. So it's getting a lot of traction now, cross-laminated timber, but also glue-laminated timber, because you could do a lot of prefabrication and we can bring parts that are already pre-milled to size and pre-drilled and openings are made, and you can bring this to site, and it's a really quick construction method. The only issue that we see now, and I'll be interested to see if you have any comments on this from the Canadian side, but I also have data in Canada. The only issue with timber, this is a great solution for having lower embodied carbon in buildings, but it usually comes with a sort of premium for wood. And if you look at the data in different places, so this is data from a couple of years ago in the UK, where the mass timber frame is, I would say, substantially more expensive, or maybe substantially in the sense that it makes a big difference in the decision, comparing to other materials that are a bit more carbon intensive. And you can see that in other articles, what is seen is that the solution that should be that is the low carbon solution is the solution that is more expensive. So it's really hard to convince clients or developers to go for timber construction at scale, since it's more expensive. And my research has been focusing on reducing the amount of structural material as a way to reduce cost. And one of the big opportunity that I saw, and this is maybe where there was some inspiration with the work of Mark West too, is that if you look at the bending moment in a beam, so a structural engineer would take a beam that is uniformly loaded and say, well, I have the maximal bending moment at the center of the beam. I'm going to design the section at the center to resist that bending moment, so that everything is going to be holding up, and then extrude that same section throughout the beam in order to simplify construction. You know it's going to be strong enough at the center, and you know it's going to be overstrung at the supports, but that's fine because it's easier to construct. But doing so, you actually waste material, and here I've written as a missed opportunity where we could actually shave off some of the material to follow the bending moment in order to make it more efficient. The other missed opportunity is in section 2 is if you were to compare this to an I-beam that maybe people are more familiar with, the I-beam will have material at top and bottom and a very thin elements connecting the two. And this is a very efficient way of using material to maximize its strength for the amount of material that you have. And if you look at how we build glulam is something that we've been using for years, but the section have been really unrefined in many ways. There's also about half of the material that's underutilized in the section in the way we utilize this. So if you combine these two in the longitudinal cross section and the longitudinal section and cross section, there's about a 66% overuse of structural material. And this is true for most materials you see around you. So if you look at structural elements around you, and especially the one in mass timber, there's about 66% of material overuse or waste. So this is a massive opportunity that we could use if we apply structural optimization and your fabrication techniques to kind of go after this material that is overused or wasted in order to reduce material use. So one of the questions could be, is it worth it to actually reduce material? Is it going to save money? And I'm going to address this in a second. But really, my research is, considering also construction methods and how we've been thinking about materials in the past. So up to the early 19th century, you can see this was actual sections that people built at the time where the cost of material was very high and the cost of labor was relatively low to the material. So it was, I'd say, worth it to put a lot of effort into creating efficient sections. So this is a section of a timber that was used, up to the 19th century. For construction of large spanning timber structures. And then at the start of the 19th century to about now, we had a lot of automation, power tools, and industrialization that kind of pushed to rationalize a bit the construction in order to save construction costs. And also with the shift in how the global markets for material sourcing, where we had the kind of balance between labor costs and material costs is shifted, where material become fairly inexpensive compared to the cost of delivering or making the elements. And my research is really questioning about what is next if we consider robotic labor to be relatively cheap, and then the cost of material having a cost on the environment, not only how much does it cost in terms of money, but also what is the impact on the environment of using materials. We are kind of reshifting the balance between cost of material and cost of labor. And my research is really asking what is next in terms of the sections that we should build out of timber. And if you look at the cost of material and the cost of structural timber, especially in state-of-the-art facilities, the wood contribution, so how much is the contribution of the wood, just how much you pay for the wood and how much the final product costs. It's about 90 to 95% of the cost. So the major cost component in making these timber elements is the cost of lumber. And as we go towards more and more efficient construction systems that are optimized or using robotic systems, like you can see here from this brand that exists, that is the product that is available in the market, the cost of manufacturing is going to go towards zero, where you can imagine very, very efficient manufacturing centers where the only thing that you put on one side is raw lumber or dimensional lumber, and then at the end you get this final product that is made. And what happens in between has very little cost because it's all using robotic systems. So the major contribution to cost is going to be material, and it is already 90 to 95% in state-of-the-art facilities. So if we can find a way to reduce the amount of material in these structures, we can actually have a pretty good chance to reduce the cost of the overall structure, and in that way making timber construction that is a lower embodied carbon material the first choice for everyday structure. So I'll apply some of these ideas to my research, and I'm going to talk about two of these today. One is going to be shaped timber beams, and then the other one is going to be hollow CLT floors, both different strategies to remove material in the elements. And if you combine these strategies into a regular master building, it can lower the total construction cost of about 6%. And in some cases, that can tip the balance in terms of competitiveness for the material. So if you apply these technologies to a master building, it could become a cheaper option than, say, steel or concrete. So this is exciting in ways that if we could push for these technologies to be deployed in construction, it would be easy to convince clients or developers to use mass timber because it would be, if not cost competitive, cheaper. So the first aspect was shaping timber beams, and I've mentioned how if you look at the amount of force and how it's distributed inside of a beam, so the inner forces, so shear force and bending moment inside a beam, you have more at the center and a lot less at the supports for bending moment, and then shear will be almost zero or zero in most cases at the center, and then going up towards the maximal shear force at the supports. And you could take that into account and kind of change the shape of a timber beam. So you can see here the original timber beam, and if you kind of optimize it to follow the amount of force that is in it, you could get a timber beam that has a slight belly underneath, where you put material where it wants to be. And some of the work that I have in the citation here has been creating the mechanical models to express the behavior of these elements that are shaped. There was some knowledge on how these shaped element behaves, but not combined everything into a coherent model. So some of my work has been working on the timber mechanics and shaping optimization in the background of this methodology here that you see, and outputs kind of the shear stress and bending stress distribution everywhere in the beam in a closed loop equation, or analytical equation. So it's really quick to perform, and it allows me to run a lot of optimization loops very quickly instead of using finite element methods or other types of design methods. And this is a simple example to kind of show how this would work. And in that case, the reduction of material volume is 8%. It's not a very big savings. So you could think about whether this is worth it in terms of the effort that you have to go through to shave that material to save 8%. But if you push this technique a bit further to more design opportunities or more wild change in the section, so you can see here that this method has been also pushed to extremes, and in some cases you can save up to 70% of material in a beam by changing how we use the material and putting material where it is the most effective. And you can see this example here of a beam that had an initial aspect ratio of 1:2, and in that optimization, we allowed the beam to kind of grow a bit in depth in some places, but also get narrower in certain other places. So you can see that at the center section A, it looks more and more like an I-beam, where the material to resist bending is going to be placed on top and bottom. And then towards the supports, this section is kind of morphing towards more like a section that is better at resisting shear forces, that has a belly at the center where you have the highest shear stress. And with this, this reduction in about 70% of material use in this element. We were also interested in exploring the design opportunities for these elements. So the idea is not to provide a tool to architects and engineers and say, optimize this beam until you find the most efficient element. But it's more about, this is an option, and you can also have agency about how you want to shape the elements. And you can, have different manipulations that some examples that you can see here, where you can have a bit of agency on the section shapes and also how much modifications you want. So sometimes it's not about having the most efficient elements, but it's about having something that also looks a bit different and more interesting. It can fulfill different functions in the building. So one example I like to talk about is this one, where this is not necessarily a massive saving of materials compared to what could be possible in the same element. But this one has, I would say, an interesting section. It has a U shape, inverse U. So the model that was developed here in this research allows this kind of analysis to calculate and design these kind of beams. And you can input a section and you can find the optimized version of the section that you want based on this timber mechanics model that's been developed. So the U section here, you can have a trench for lighting or some other systems, but you can also decide to have simple modifications based on the kind of fabrication techniques that is available to you. Sometimes it will be difficult to manufacture this. It will be easier to just change the height of the beam or the width of the beam. And you can still get pretty significant savings of maybe 15% reduction if you had changed the width of an element. Or you can go for more complex sections like these at the bottom that has either bigger savings or more interesting kind of aesthetic or design features. Another important aspect of construction that my research looked at is floor plates. And one of the reasons why we looked at floor plates more carefully is because it is, in a lot of buildings, the majority of the structural material. So in mass timber buildings, if you look on average, about 80% of the total structural material is in mass timber is the floor plate. So the CLT, the cross-laminated timber panels, represents about 80% of the structural material in the building. And beams and columns are about 10 to 15%, depending on what kind of structural system is used laterally and the size of the building. But in a lot of cases, the cross-laminated timber panels that is considered so convenient is also what is contributing so much to the cost of the building. So the research looked at how we could optimize this panel to be more materially efficient. And I don't know if you ever played Jenga, where you push sticks of wood out of a tower. This is kind of the same idea here, where we decided to question what would happen if we were to push some of the cross layer in CLT elements and see how it would behave. So in CLT, the cross layer typically is not used structurally too much. It is true that CLT has a two-way capability where it can carry loads in two directions because it has fiber running in two directions. But due to transportation constraints, typically the CLT panel is used as a very large and wide beams because it has no connections between on the side, so it's not able to activate the two-way system as much. There's a few projects that exist where CLT has been used as a two-way slab, for example, the Broxcommon at UBC campus. But due to transportation constraints, you have to have a very tight grid space to enable this two-way action. So here we were considering only one-way bending, so panels that act as a wide beam. So the cross layer is structurally useful as a way to space between as a spacer between the longitudinal layers, but it's not so much of use in terms of the structural strength. So here the question was, how can we change these panels by playing Jenga with them? And what was interesting here that I'm showing a case where I'm removing every other elements, but there's a potential for mass customization where you could have more elements towards the ends and less at the center, where you have more shear forces at the supports. And the other interesting aspect is this is a very minimal change to current manufacturing process, where we've been in touch with manufacturers and they could manufacture these panels tomorrow because this is already possible, and some of them already do that as part of the manufacturing process. So the question here is like, how much can we remove without having a panel that is not structurally sound anymore, but still enough to have an impact on material savings? So this is an example of the results. My research looked at building a structural mechanics model for the behavior of these panels in a full closed form. So again, that would be really fast to solve, and you can use an optimization. And here is a graph of the stiffness to weight ratio of these panels if you poke some holes in them. And at the bottom axis, you have from 0 to 1 is the relative density of the cross layer. So 1 would be a full panel, and 0 would be a panel that has all the cross layers removed. And 50 would be this image here where every other element is removed. So this is the variations of how much we remove in the cross layers, and this axis here is the stiffness to weight ratio. So how stiff it is compared to its weight. And what is interesting to see is that the actual range of optimal values is below 1 in terms of relative density of the cross layer, meaning that it would be much more efficient in terms of material use to have panels with holes in them. You can see that the optimal ranges is between 30% and 60% of the cross layer, meaning that you want to remove either 60% or 65% of the cross layer, or 25% of the cross layer. That would be the optimal in terms of how stiff the material, the panel is compared to its weight. And we looked at stiffness specifically because it is a better proxy in terms of structural capability for these panels. Most of CLT structures of panels are governed by stiffness or displacement constraints. So you want to make sure that the panel stays stiff enough, and the strength will not be an issue as much. Even though we looked at stiffness here, the strength was always part of the calculation. So all these panels are structurally sound in the sense that they can support the load, but also be stiff enough. And we performed some structural load testing, as you can see here, an example of a panel that has like one of every other element removed. We did some bending tests and compared to them full panels. And what you can see from the results is that the black lines would be standard CLT panels that have the full cross layers, and the blue lines would be the optimized version of the panel. That means without some of the cross layer. So what you can see is that the optimized panel is less stiff and less strong than the full panel that has a bit more stiffness. So this slope here is a bit higher, and it goes a bit higher in terms of force. But what is important to remember is that this consideration of the stiffness to weight ratio is important too. So the optimized panels are a bit less stiff and less strong, but they also are a lot less lighter, or heavier. They use a lot less material. So in terms of the maximization of the use of material, they are a lot more efficient. And this was the first part of on materials and building elements. And I'm happy to take some questions now to kind of break out the presentations in chunks if you have any burning questions before jumping into building systems.
Hello, Paul, can you hear me?
Yeah, I can hear you.
Hi, my name is Cesar. I have a question on the beams. Maybe you will address it later, but how did you take into account waste or no waste when it comes to beam optimization? I guess you see where I'm going with the question. If this was a subtractive process and the material is being removed after the beam was made, then all that material is still being used, just going to waste. But maybe it's an additive process. And what are the chances that the rest of the material is actually used for something else? Thank you.
Yeah, that's a great question that is very important to consider. So, of course, if you want to, make this efficient beam, but you waste a lot of material, that would be not really, a good way to save material, because you will have to mill. Let's say you will have to make a big block of wood and then mill it away to get this efficient shape. And the question is, what do you do with the sawdust? So we did a couple analysis on, what is the value of structural lumber and what is the value of sawdust, and we compared like a standard beam into, if you used structural wood into a non-efficient beam, and then structural wood into a block that you mill down, and then you reuse the sawdust for energy use, so you can burn it. And in most cases, this analysis shows that even though it seems wasteful in terms of financial calculations, it still makes sense to have more efficient structural systems and even produce a bit more sawdust, but reuse it for energy production. But intellectually, it's not super satisfying as a system, because you would want to, find a way to combine fabrication techniques with the shapes that are optimized. And this is something we're actively working on now. And I wish I could show some images, but we are about to publish a paper where we found a method to create this optimized beam without any waste by combining layers together. So you can use a pattern for cutting some layers, and that you produce no waste. I don't have any images for this, but once this is ready to publish, I'll be happy to follow up if you want to see it.
Great, thank you again.
I'm happy to answer any questions, or I can continue if there's any burning questions now. I guess when I mentioned burning questions, sometimes questions I get about this optimization technique is how is fire considered in mass timber elements. So maybe some of you know mass timber is resisting fire by adding a bit more mass around the structure. So the beam would char, and the char would protect the inner beam from the outside by kind of insulating the inside of the beam. So in the examples I showed, we didn't activate the fire considerations, but in the system that we built, or the methodology that was built, the fire was taken into consideration for the design. So you could activate the fire considerations, and it would produce thicker beams, or take into account the fire load case and the design of the optimization. So if there's no question at the moment, I'll just move on to building systems. And this is the second scale of consideration for low carbon timber structures, when we combine different elements into a building system. And part of the reason I mentioned it earlier is that there's a lot of digital fabrication that is enabling us to build complex timber structures, or complex structures in general. And you can see here some examples of recent structures that have been built. Highly complex structures that are super efficient. But I think the issue in some ways is that these are not super applicable to everyday structure. And if you want to have an impact on the environment at scale, we want to impact everyday structures. So that was a bit of the issue here. And part of what we looked at is how we can also expand the design options. And I think one of the questions we had early on is we don't want to create an optimization system where, for everyone is going to have the same beam shape, because everyone wants to optimize inside material where you have one bending moment in that case, but you can have only one beam shape. And the idea was more to open design opportunities at the same time as saving opportunities for material. And when we started combining different structural elements into structural systems, we looked at indeterminate structure systems that has, I don't know how familiar with indeterminate structures, but pretty much there's a bit more, you can use structural tricks to change how the bending moment is being distributed in the element or the structure. So we use that to kind of shift towards having many bending moment options, meaning that we can also turn that into many different beam shape options in terms of the savings, but also the structure aesthetic. And this work resulted in a publication that you can see here, but also this image that was kind of showcasing, you can see the structure on top. That doesn't look like a typical bending moment diagram. If you see like this double bellies in the beam. And here we decided to kind of shift the shape of the beam towards something that we thought was interesting for the space, instead of going for the most optimal solution. And in that case, I think it was interesting to go away from the most optimal solution, but also have a bit of agency on how we control the optimization. And we pushed this to different structural systems. So here is this idea of using shaping on indeterminate frame structures. And this is a frame from the book by Heino Engel, Structure Systems, where we applied shaping. And you can see that starting from the standard frame here, we reference this as 100% material usage, that you can find different shaping options. Some of them are more efficient. So you can see here 85% material usage, so a reduction of 15% of how much material is being used, and you get these shape options. But you can also say, I don't really like this one. I like something more like this, which has some shaping in it, and maybe you don't get as much saving, but at least you know how much material you're using, even though you're changing the shape of the structure. Or you can take something that you prefer more for other reasons or other constraints in the design of fabrication. In that case, it's using 25% more material, which is fine in some cases, as long as you're aware that this is a decision and you can take that decision backed up by numbers. So here, we made 6 options, but the methodology was enabling us to kind of decide on multiple design scenarios, and at the same time knowing how much material there would be. And all these solutions are structurally sound in the sense that they have a limit on how much they move and how much displacement there is in the structure, and make sure they can all take the same load. Another structural system development that I've been working on is efficient floor systems. So this is something that I'm currently doing as a resident at Autodesk Pier 9 in San Francisco. So Pier 9 San Francisco is a state-of-the-art fabrication space that was designed and built by Autodesk, the software company, to enable researchers and makers to come in and try tools to push ideas in construction or making communities. And I'm currently a resident there, where I'm developing this efficient structural system. And here's a comparison between the two. So on the left, you have a standard cross-laminated timber and glulam systems that has like beams on the edge and then a panel on top. And then the proposal here is a hollow core panel system that has prefab modules. And these modules, you can also incorporate thermal and acoustic insulations inside. And it will be about 50 to 60% more efficient some of the material. And you can see here an early prototype that was finished a couple of months ago, where the system is only column supported, so it's point supported. There's no load-bearing walls, which allows for a bit more architectural freedom. And what was super interesting here to the team is that if you imagine that panels have a transportation limits and how wide a panel can be transported. So it has, I mentioned that earlier, if you want to do a CLT structure and use a two-way capability of CLT, you have some limitations on how wide the column grid can be, because the truck is going to be a certain width and you can't really exceed that. And then you have to take that into account. So here where the system takes an advantage to this kind of triangular pattern, where if you look at the depth of the triangle here from this tip to this base of the triangle, that would be the maximal width of transportation that is allowed in a certain place. And then by using these cross diagonal beams, you can actually double the span that is possible with efficient systems by using this kind of triangular system of panels. So the panel would be prefabricated, and then you would bring on site this kind of cross beams that you assemble there, and then put the panels in, and you would get a very large spanning structure out of timber that would also have a lot of insulation and acoustic advantages. So here's a render of a possible unit. This was developed in collaboration with Fabric Workshop and Hacker Architects. The idea of the system was to be used in affordable housing and residential housing to lower the cost of timber construction. But here the render is more of a high-end unit. When we first tried to get this built, we were trying to appeal to the first something that would be a bit easier in terms of finances. So here's like a more high-end residential idea. But you can see the potential of having this longer spanning structures and some of the interesting design features that could be used in terms of opening some triangles and having some openings in the system. And what was interesting too is not having any load-bearing walls, so everything is supported in columns. That gives a lot of freedom in terms of the space. So some of these findings have been published in this book that I helped write with FT Architects in Japan, where this book looks at the history of timber construction throughout the early modern period in Germany, and we contribute an essay in what is the future of timber construction and how digital fabrication can support that. And I'm kind of going into the third scale of design here. So I don't know if there's any burning questions on this part in the building systems. Otherwise, I'm happy to go through the next part. Okay. So this is more related to the work I'm doing now at UC Berkeley, and it's really how we consider forests into building designs. And I think if you look at CLT or mass timber buildings, typically they have one type of wood that is used throughout the building. But if you look at forests, they are not really one type wood in the forest. There's like a diversity of trees in the forest that is not really considered when we use them in buildings. So the question I'm asking here is like, how diverse are material sources put to buildings, and how we can consider the diversity of materials from our ecosystems into buildings. And this is a picture from a famous bridge on Big Sur. This was a couple of months ago, and fires are part of the ecosystem in California, but also has been part of the issues recently because the fires have taken such a big scale and impact. That is typically not the case. And the other issue with this picture is that this was taken in January 2022, which is supposed to be the rainy season in California, and you can see that this wildfire is happening. Wildfires are a big issue, and part of it is because we have a lack of forest management that's been happening for the last 100 years. So in the state of California, there was this 10 a.m. rule that was imposed on the forest, where for the last 100 years, every fire that was happening had to be put out by the next morning at 10 a.m. And this has led to build up the forest in terms of biomass, in the way there's a lot of shrubby or tree or smaller trees that are kind of populating the forest without letting the fire as a natural way to clean the forest and let the bigger trees grow without competition. So there's a need for increase of forest product utilization. That means that we need to get wood out of the forest because we have this backlog of about 100 years of management work to do. And this is about 20 million acres of forest that needs to be treated, meaning that it is to be mechanically thinned, so cutting down the smaller trees or using control burning to reduce the amount of biomass in the forest, especially the smaller, thinner trees. And doing these operations usually results in low value wood in underutilized timber species that has little value on the market. And if we can't find a value for them, it's really hard to have the resources to go and treat all this 20 million acres of forest. So the work I'm conducting now is trying to find use for small diameter timber, but also hardwood species that are considered as weeds, and how we can use them in architecture and engineering. So I've been developing the California Undervalued Timber Center with some colleagues at UC Berkeley, where we look at the suitability for local California hardwoods for architecture and engineering wood products. And we've only focusing on oaks at the moment, and also blue gum eucalyptus. And our focus has been on veneer-based products. So instead of having to mill the log into dimensional lumber, we're looking at newer technology that can peel the tree into thin veneer, which has advantages in terms of how much energy is needed to dry the wood because it's much thinner. And so you can dry it much more quickly, but also you don't have as much waste in terms of production. You can see here on the pattern on the left, sawing a log will result in a lot of sawdust, and which is not the case for veneer production. And finally, using the newer technologies in terms of lathe for veneering trees, you can access much smaller diameter trees that you can actually recover some fiber from it. Because if you try to get a 2x4 or 2x6 out of a small diameter tree, it's going to be really hard, but you can get quite a bit of veneer from it with the newer technologies. And another issue in California outside of the fires is the spread of diseases. So here you can see the spread of southern oak death in the state in yellow. Sorry, this was supposed to be yellow. You can see that it's been spread throughout the different counties in the state of California. And you can see that black oak is one of the species impacted by this southern oak death. So there's also a need to clear out some of those trees that are in the forest because they are going to die. And if we don't use them, they're just going to rot in the forest. So part of the engineer research happening in Australia has been very useful in deciding on how to go next. They've been doing a lot of work on small diameter and veneering of small diameter trees because they have the same issues in terms of wildfire. So here you can see some of the work that's been developed in creating structural efficient elements out of veneered or molded elements. And part of the research we're looking at is pushing this towards new directions of either fabrication techniques that could be applied for architecture and design. And here I'm showing an example of this, like explained by the EAMS, where we could create like molded structurally efficient elements, and then pushing this towards optimized building elements in some directions that would be both using local forest elements that has to go, and also efficient structural elements that would make the best out of these resources. So currently developing the center here, we can see some of the ideas that we have, and we built a experimental solar kiln. So we want to be able to treat everything from getting a tree to a final product, where we have the ability to dry wood, store it, condition it for veneer, and then we can use the lathe to veneer the trees, and then we have some vacuum presses. So some of it is in development and we're getting money for this, but some of it is happening already, where we're trying to build up the capabilities of the center at UC Berkeley. So here's an example of the geodesic solar kiln prototype we built last year to dry local hardwoods using only the energy of the sun. And we have an ongoing project where we want to build multiple of these solar kilns throughout the state and kind of customize them based on the volume of production needed. So this is a structural efficient system. So the geodesic solar kilns will be very efficient to scale, or easy to scale, due to the structural efficiency of the system, but also change the different thermal aspects of the construction depending on the wood species that needs to be dried and the location and climates of the elements. And part of the work we've been doing too is collecting and building a library of local hardwoods for processing into small beams and testing them to get knowledge on the structural behavior. So here you can see a picture of the early stage of the collection, where we have some blue gum eucalyptus that was collected on campus, and then some black oak and madrone, and then we've extended to different oaks that we have worked with mills throughout California to harvest and dry for processing. And some of the work on small diameter timbers or rod construction has already kind of made into practice. So this is an article that we wrote with some colleagues in the UK and in the US about whole timber construction. So using timber in its round shape in order to minimize processing. So part of these ideas have been transferred into this design competition here, where I was a consultant for this design project by KVA in Boston. And here's an example of a master thesis at MIT that happened last year, where the student was trying to empower the local communities to use the local forest resources in order to avoid buying materials from a store if you could just access it. So what can you do with wild or round wood in your community? And I think that was interesting here that the student kind of made this IKEA-like manuals where you have a set of tools, what kind of resources you have in your area, and you can kind of follow it step by step to create, in this example, like a wall element using slabs and branches to create like a construction element for your community. So I'm going towards conclusion. If you do research, just as a reminder, my research has been mainly focusing on asking the question, what is next for timber construction, looking at this imbalance or balance between the cost of construction and the need for efficiency. So labor and construction material cost has shifted throughout the years, and it's different in different countries. But I think now we are in a situation where we need to think about ways to reduce the environmental cost of our buildings. And at the same time, that means that we need to reduce the cost of construction of mass timber so that it becomes the one solution that is easy to take, because it will be cheaper than other systems. And that can be leveraged through digital fabrication, but also structural optimization. And part of these concepts, I think, could be included in a larger forestry frame kind of idea. So the agriculture movement have been really successful at connecting farmers to the final table where food is eaten. And here you can see a timeline of all the steps that have to be taken in order to connect the final consumers to the source of the product. And I think we still have a lot of work to do in construction to make a more direct connection between how we use our materials and how they were produced. and who's producing them too. So finally, I wanted to reiterate that my interest in research is to push materials, architecture, design, and engineering to new carbon efficiencies, combining these three research areas or research interest in the idea that we could build more efficiently, but also create construction systems that are sustainable for the future. Thank you, and I'm happy to take any questions now.
Wonderful, Paul. Thank you so very much. So we do have a few minutes for a couple questions here. I'd like to open the floor up to anybody who has a question for Paul. We also have a chat if you have something you want to ask that way. Okay, David has put up a post here. It says, this has been one of the best presentations that I've witnessed that clearly presents the means and methods of structural design and construction. Excellent.
Thanks, David. Maybe
I'll probe a little bit here, Paul, if that's okay, while people are sorting their minds out here. So it's really exciting to see how you've been kind of merging trajectories in technology to think about ways that we can work with existing strategies for creating greater efficiencies, right? So some of that is through digital tools to map forces. We know generally, especially for simply supported beams like this, that we know where the force flow is. And then you're also sort of hybridizing different strategies for creating lightweight and stronger structures. Like I'm thinking of torsion boxes and using hollow grids and monocoque shells and so forth, but then applying it to a mass material technology, which is very interesting, right? It seems like, of course, that makes a lot of sense. How can we introduce voids in these massive elements? And I'm wondering, though, what's interesting is that the linkage here and the similarity of the work that Caitlin does, of course, at MIT, and the work you're doing is this idea that the bridge between the optimization question, how to make more efficient structures, and the role of the designer is that shaping structures is the middle ground there. It's actually form that is the thing that links us as designers to greater efficiencies and thus a greater impact on cutting our carbon footprint in production, as you pointed out. So I'm wondering, from your perspective, if you zoom out of this whole sort of approach, and could you describe a little bit about what you see the opportunities for creating greater dialogue between the designers involved in shaping structures like this, the digital tools that play a role in helping to reveal how efficient shapes can be, and the structural engineers who are partnering on a project who can actually create a dialogue and conversation, which otherwise might not happen without tools like this. I'm just wondering how you see this approach creating opportunities for more conversation between structural engineers and designers.
Yeah, thanks. That's a very good question, and something, I guess a lot of us are working on in some ways, and, making that connection. And it's true that this, timber beams, as we've seen in the presentation, could have a lot of potential savings, but it's not the most impactful, but it has a lot of impact in terms of the aesthetic of the building. And I think, it has some pretty complex timber mechanics in the background that it will be really hard as a conceptual level for, everyone to kind of like use on a piece of paper to sketch. But I think what is interesting is just, at a first step, using this idea that there is the possibility of doing this in structural design, or you don't have to be very precise, but you can just sketch the idea of this is what we want to do, and then there's another step where the design process evolves and there's a bit more analysis that has to be done that could be part of the engineer's work. But so, for example, we're doing a small project now for a private house in Cambridge, where we're going to have a shaped timber beams. And part of the discussion where there was not necessarily, let's find the most optimal version of the beam. That would be maybe the engineer's job. And that would be in a very extreme case where the optimality is what is, necessary maybe for the economics of project, or maybe something else is driving your project. In that case, it's more about what is the gesture of the structure and what do you want to achieve with that. And, you know, the discussion on does it work structurally or not is coming way after, because it's, you know, you can still modify it, and if one is open to small modifications, you can get to a final design. But I think the more gestural aspect of it, and it's where the work on indeterminate systems came in, where we wanted to make sure that we can still keep options open in terms of how the structure looks like, and it doesn't have to be guided through the optimization. That would be kind of a black box way of approaching design. So it's more about, you know, what is the intention behind it, and then how can we achieve this later on with the tools. And what's connecting the two here is, you know, an optimization tools that could be either very flexible for, you know, the conceptual design level, where it's not so much about finding the most efficient beam, but it's about giving options. And then there's another version of the tool that's like, it has to work as a structure, so let's make sure that it's not going to like fail or misbehave like we didn't intend to.
That's really fantastic. It's interesting because it links together with one of the first slides you have of Santiago Calatrava's train station in Zurich, where in the ground level there's these custom-made concrete piers and support columns that are quite, I guess I'll use the term organically formed, then curvilinear in shape. And then upstairs is the steel frames, which are much more, I'd say, slender and elegant. And but I think that this approach, what is exciting, at least to me, is this idea that very often the conversations with structural engineers from designers' side and architects specifically has traditionally been surrounding the question of dimensionality. How deep is the beam? How wide does it need to be? How heavy, and so forth. But now we're talking about a possibility for this approach to shaping structures, and specifically with wood, that is more plastic, say, than steel traditionally has been in terms of rolling off lines and so forth, that actually the conversation between architects and structural engineers specifically can now become much more qualitative and conversant, especially at earlier design stage. At least that's what it seems like from what you've presented.
Yeah, and I guess what I'm thinking about now is like, what would be interesting is I would be wanting to get people excited about this so that, it becomes something that people want to design with. And it doesn't have to be most efficient, even if it's for the beams, because they actually, no matter what the beam is, not going to have a massive impact on the total structural volume, because the panels are the most important, and the panels, you don't really see what's happening. So you could even have one of the least efficient beam that you want, but it's part of the design, and then, have a super efficient CLT panel on top, and it would still get a lower construction cost. And you would, either have best of both worlds, because you have a lot of design freedom and how the structure looks like, but you can also have high efficiencies, or you can combine these in different manners. But I think just having the ability to have the conversation and the numbers to back it up is, so you can take informed decisions on the design decisions.
Wonderful. Thanks, Paul. Are there any questions? I know we're running a little late here, but we have time for one if there is one. Okay, well, we are past 1 o'clock, so I will officially thank you, Paul, very, very much for this wonderful lecture. It's really exciting to see the progress that you're doing. And as I mentioned previously, Paul, your workshop on structural shaping will be on May 9th through 11th, I believe it is. Is that right?
Yeah.
And that's going to be a 3-day workshop, and we will be sending out some information and a poster on that in short order. And you'll be able to hear more about that, Paul's research during that time. And Paul's going to be offering valuable lessons on design tools, specifically digital tools that can be used for optimizing structural forms. And we will be collaborating with the Fab Lab on that so that we'd be able to construct some of the output from that workshop. Okay, thank you so much, Paul. Thank you, everybody.
Thank you so much for having me.
It's wonderful.